Greetings. Today we're going to talk about the universal gravitation. I want to give you a little introduction to the equation, where it came from, and how to use it. It's going to be really important here to pay attention to exponents and to use your calculator correctly when using exponents. So to do that, you're going to have to hit the second button and then the button with the comma on it so that you get the small size capital E that means 10 to the x for your TI. All right, so in 1665, Newton, Sir Isaac Newton that is, went away from Cambridge to live with his mom at home in the middle of nowhere because the plague was sweeping through England. And during that time, he did a few small things. He invented the calculus. He came up with his theory of light, how optics work, and came up with his force laws, and he came up with something called the universal equation for gravitation. Now this explains all the stuff that we've been doing throughout the fall about weight and the force of gravity. What I've written right here is the equation for universal gravitation. So the F with a little tag G below it stands for force of gravity. Capital G is a constant. It's always the same number. It's 6.67 times 10 to the negative 11 newtons times meters squared over kilograms squared. Those units just make the equation give you an answer of force in newtons. M1 and M2 are the two masses you're talking about, because it doesn't matter whether you're multiplying 2 times 3 or 3 times 2, you get the same answer. When you're solving equations, you're going to have two masses. It doesn't matter which mass is M1 and which mass is M2. R is the distance between the two masses. Newton historically used an R for radius because he was really paying attention to the distance between the moon and the Earth and the sun, which was the radius. So he used an R. If you look this up in other places, online or other textbooks, sometimes it's a D. But what matters is that it's a distance. It's got to be in meters, and it's squared. So let's just do a quick sample problem to give you a sense of how this works. Okay, so we're going to start with a problem at the zoo. We've got a 1,800 kilogram elephant and a 1,600 kilogram hippopotamus, and they're 3.4 meters apart. We want to find the gravitational force between them. So obviously we're going to use the equation for force of gravity. It does not matter which mass is which mass. So you just do this as a simple plug-in. We're going to say F is going to equal 6.67 times 10 to the negative 11 newtons times meters squared over kilograms squared. So that's, I'm going to put the whole units in so you can see what we're doing here. We're going to multiply this by 1,800 kilograms, that by 1,600 kilograms, and then we're going to divide the whole thing by 3.4 meters squared. I'm going to pause right now. You figure out the answer yourself to make sure you're using your calculator correctly, and then we'll continue. Okay, I got 1.7 times 10 to the negative 5th newtons. You should have gotten something similar rounded off to two significant figures. Notice the units now. If you see, we have a meter squared here. That's going to cross out with these meters squared. We have a kilogram and a kilogram. That's going to cross out with these kilograms squared. That leaves us with newtons. So you get an answer in newtons. So again, you should get 1.7 times 10 to the negative 5th newtons. If you got something really close, like 1.8, 1.6, don't worry. If you didn't get that, try it again in your calculator. Make sure that you're using 6.67 second, the comma button, so the E comes up, and then a negative 11 in your calculator, and then you multiply by 1,800, you multiply by 1,600. You might want to get an answer to that part, and then divide by 3.4 squared. Okay, I've just typed out a bunch of numbers that you're going to find useful for the next couple of weeks. You do not have to memorize these. I repeat, you do not have to memorize these, but I'm going to use them in a variety of problems and examples over the next couple of weeks, and I'm going to use some right now. So you may just want to have them written down or get easy access to them. You can, of course, Google them because they're just factoid numbers. Okay, crucial thing. When you're doing universal gravitation, you need to use the distance between the center of the two objects. Now, when we're talking about people or animals in the zoo, the difference between the center and the outer edge doesn't really matter. But when you're talking about a planet or a moon or something large like that, it's a very important difference. So let me just give you an example about some key words we're going to use. The word orbital radius, which I've used in some of these examples above, equals the center to center distance. So when I said Earth orbital radius above is 1.5 times 10 to the 11 meters, the Earth orbits the Sun. That number is from the center of the Earth to the center of the Sun. That's the number that you would use if you were doing a calculation about the force of gravity between the Earth and the Sun. I gave you the Moon-Earth orbital radius. So what is that? That's the distance from the center of the Moon to the center of the Earth. Not the outer edges. It's the center to center. Right? That's important. So let me give you an example. Let's say we were talking about a case where there was a satellite that was a certain height above the Earth's surface. So here's the Earth. And I told you there was a satellite that had an altitude, and I'm just going to say that altitude of the satellite is h. So in other words, that's how high above the Earth's surface the satellite is. If we wanted to do a gravitational calculation between the Earth and the satellite, we wouldn't not use the altitude or the letter h by itself. Instead, we would have to do the following. If this is the Earth's radius, we would have to add the Earth's radius to the altitude of the satellite, and together those things would make the orbital radius, and that would be the center-to-center distance, and that would be the thing we would use when doing a gravitational calculation. So again, you always have to use the center-to-center distance. Before we do that problem, let's do another just sort of example where we don't have to do anything fancy, but just use big numbers. So right now we're going to figure out the force of gravity between the Moon and the Earth. So find Fg between the Moon and the Earth. So you do that. I'm going to pause this, and when you come back, you should have an answer, which we can check with mine. Okay, I got about 2 times 10 to the 20th, to be exact, 1.99 times 10 to the 20th to 3 significant figures. This is a case, again, where you really have to pay attention to the exponents. If you didn't get this, go back, make sure you have your exponents put in the correct order, to the correct power, that you're using the second comma button to do the exponents. Make sure that you squared the distance on the bottom, and make sure that the order of operation is all worked out so that you didn't mess up something in your calculator, because I'm confident that this is the right answer. Now let's do a slightly more complicated problem. Now we're going to do the following. A satellite is orbiting at an altitude of 4.62 times 10 to the 5th meters above the Earth's surface. It experiences a gravitational force of 3.8 times 10 to the 4th newtons with the Earth. What is its mass? Okay, so you solve this problem, and hit pause now, and after you're done solving it, I'll show you how to do it. Okay, so first of all, let's look at the equation and think about what we're looking for. We're looking for mass. So in this equation, F equals big G m1 m2 over r squared. We need to get one of the masses by itself, and it really doesn't matter which one. That's completely irrelevant. So I'm going to arbitrarily say that the satellite is m2 and the Earth is m1. So I'm going to get m2 by itself. So the first thing I'm going to do is multiply both sides by r squared. So I would get F times r squared equals G m1 m2. And now I'm going to divide both sides by G m1. So I'm going to get F r squared over G m1 equals m2. So now I've got the thing that I want by itself. The other thing you need to see is this is a case, like what I mentioned a few minutes ago, that we don't have the radial orbit, or the orbit of radius. What we have is a altitude above the Earth's surface, and we need to add the Earth's radius to that. So for the r squared term here, we need to add the Earth's radius plus the altitude. So we're going to add 6.38 times 10 to the 6th meters plus 4.62 times 10 to the 5th meters, and that gives us 6.44 times 10 to the 6th meters, and that's what we're going to use for r in this equation. The g we know, the m1 is going to be the mass of the Earth, and the force is the 3.8 times 10 to the 4th newtons that I gave you in the problem. So now we're going to solve the problem. So we're going to rewrite it like this: m2 equals f times r squared over gm. Now you plug that into your calculator and see if you get the same answer I do. Okay, so I got 3,951 kilograms. That's 4 sig figs. I need to have it to 3. So I'm going to rewrite that as 3.95 times 10 to the 3rd kilograms. That's a very reasonable mass for a satellite. Notice why the units come out to kilograms. If you look up here, you got a newton, crosses out with a newton. I got a meter squared there, gets rid of these meters squared. This kilogram gets rid of one of these kilograms, so I'm left with 1 kilogram in the denominator of the denominator, which makes it the numerator. There, you now understand the basics of using universal gravitation.